situations where grounding to cold water pipes is prohibited, several effective alternative grounding methods exist. These alternatives ensure electrical safety in compliance with the National Electrical Code (NEC) and local regulations. Firstly, the grounding electrode system (GES) involves a network of conductive rods, plates, or wires buried underground. Typically, these rods are driven into the earth, maintaining an 8-foot separation, and are interconnected using a copper conductor. Secondly, ground rings consist of a continuous loop of conductive material, commonly copper wire or tape, buried around the perimeter of a building. This loop is usually trenched approximately 12 inches below the surface. Thirdly, ground plates are conductive plates, often made of copper or stainless steel, buried vertically in the ground to maximize contact area with the earth. Fourthly, a grounding well involves drilling a hole into the earth, filling it with a conductive material such as bentonite clay, and inserting a grounding electrode, which is then connected to a grounding conductor. Fifthly, the concrete encased electrode features a conductive wire or rod encased in concrete, providing a durable and permanent connection to the earth. Sixthly, if available, connecting to the grounding system of a nearby utility, such as the electric company, is an option. However, this requires permission and coordination with the utility company. For enhanced redundancy and reliability, combining two grounding methods is advisable. Examples include 2 ground rods combined with a grounding electrode system, 2 ground rods combined with a ground ring, or 2 ground rods combined with a concrete encased electrode. The selection of the most suitable grounding method depends on factors such as soil type and local regulations. Consulting with a qualified electrician or engineer is essential for the proper design and installation of the grounding system. It is critical to ensure that the grounding system adheres to the requirements outlined in the National Electrical Code (NEC) and all applicable local codes. The goal of any grounding system is to provide a low impedance path for fault current to return to the source. This low impedance path facilitates the operation of overcurrent protective devices such as circuit breakers or fuses, which will then interrupt the flow of current in the event of a fault. Proper grounding also minimizes the risk of electrical shock to people who may come into contact with energized equipment or conductive surfaces. Grounding electrode system (GES) is a comprehensive method that uses multiple grounding electrodes to create a robust grounding network. When installing a grounding electrode system, it is important to consider the soil conditions. Soil resistivity significantly impacts the effectiveness of the grounding system. High soil resistivity increases the impedance of the ground path, which reduces the effectiveness of the grounding system. To mitigate the effects of high soil resistivity, multiple ground rods can be installed in parallel. The National Electrical Code (NEC) specifies the requirements for the size and type of grounding conductors and grounding electrodes. The size of the grounding conductor is typically based on the size of the service entrance conductors. The grounding electrode must also meet specific requirements for its size and material. Ground rings offer a continuous grounding path around a structure, which helps to equalize the ground potential and reduce the risk of ground loops. Ground rings are particularly effective in areas with poor soil conductivity. They provide a low impedance path for fault currents, ensuring that overcurrent protective devices operate quickly and effectively. Ground plates provide a large surface area in contact with the earth, which helps to reduce the grounding impedance. They are particularly useful in areas where it is difficult to drive ground rods due to rocky soil or other obstructions. Grounding wells are an effective method for improving the grounding impedance in areas with poor soil conductivity. The bentonite clay used in grounding wells helps to retain moisture and improve the contact between the grounding electrode and the earth. Concrete encased electrodes, also known as UFA grounds, are a very effective grounding method because the concrete helps to maintain a consistent level of moisture around the grounding electrode. This helps to reduce the grounding impedance and improve the overall performance of the grounding system. Utility grounds can provide a reliable grounding connection, but it is essential to coordinate with the utility company to ensure that the connection is made properly and safely. The utility company will typically have specific requirements for the size and type of grounding conductor that must be used. When combining grounding methods, it is important to ensure that the different methods are properly bonded together. This helps to create a single, unified grounding system that provides a low impedance path for fault currents. The bonding conductors must be sized appropriately to carry the maximum fault current that is likely to occur. Regular inspection and testing of the grounding system are essential to ensure that it is functioning properly. Grounding impedance measurements can be used to assess the effectiveness of the grounding system. If the grounding impedance is too high, additional grounding electrodes may need to be installed. In addition to the methods mentioned, it is important to ensure that all metallic components of the electrical system are properly bonded together. This includes metallic conduit, equipment enclosures, and other metallic parts. Bonding helps to equalize the ground potential and reduce the risk of electrical shock. The National Electrical Code, NEC, provides detailed requirements for bonding electrical systems. It is essential to follow these requirements carefully to ensure that the electrical system is safe and reliable. In areas with corrosive soils, it may be necessary to use special grounding electrodes that are designed to resist corrosion. These electrodes are typically made of materials such as stainless steel or copper-clad steel. It is also important to protect the grounding conductors from corrosion by using appropriate coatings or wrappings. The grounding system should be designed to accommodate future expansion of the electrical system. This may involve installing additional grounding electrodes or increasing the size of the grounding conductors. It is important to plan for future growth to ensure that the grounding system remains effective as the electrical system expands. When installing a grounding system, it is important to avoid creating ground loops. Ground loops can occur when there are multiple ground paths between 2 points in an electrical system. Ground loops can cause noise and interference in electronic equipment. To avoid ground loops, it is important to ensure that there is only one grounding point for the electrical system. Surge protection devices, SPDs, can also be used to protect electrical equipment from damage caused by voltage surges. Surge protection devices should be installed at the service entrance and at other critical locations throughout the electrical system. Surge protection devices can help to divert surge currents to ground, protecting sensitive electronic equipment from damage. It is important to select surge protection devices that are appropriate for the voltage and current levels of the electrical system. Regular maintenance of the grounding system is essential to ensure that it is functioning properly. This includes inspecting the grounding electrodes and conductors for corrosion or damage. It also includes testing the grounding impedance to ensure that it is within acceptable limits. Any damaged or corroded component should be replaced promptly. In addition to the National Electrical Code, NEC, there may be local codes and regulations that apply to grounding systems. It is important to be familiar with these local requirements and to ensure that the grounding system complies with all applicable codes. The local electrical inspector can provide guidance on the local requirements for grounding systems. Proper grounding is an essential element of electrical safety. A well-designed and properly installed grounding system can help to protect people and equipment from electrical shock and damage. It is important to take the time to design and install the grounding system correctly and to maintain it properly over time. When working on electrical systems, it is important to follow safe work practices. This includes wearing appropriate personal protective equipment, PPE, such as gloves and safety glasses. It also includes de-energizing electrical equipment before working on it whenever possible. If it is not possible to de-energize the equipment, it is important to use appropriate insulating tools and to follow lockout-tagout procedures. Lockout-tagout procedures are designed to prevent accidental energization of electrical equipment while it is being worked on. The National Electrical Code, NEC, provides detailed requirements for safe work practices when working on electrical systems. It is important to be familiar with these requirements and to follow them carefully. Electrical safety is everyone's responsibility. By following safe work practices and by ensuring that electrical systems are properly grounded, we can help to prevent electrical accidents and injuries. Remember that working with electricity can be dangerous. If you are not qualified to work on electrical systems, it is important to hire a qualified electrician. A qualified electrician has the knowledge and experience to work on electrical systems safely and effectively. When selecting an electrician, it is important to choose one who is licensed and insured. A licensed electrician has met the requirements for education and experience that are set by the state or local licensing board. An insured electrician has insurance coverage that will protect you in the event of an accident or injury. It is also important to check the electrician's references and to ask for examples of their previous work. This will help you to assess the electrician's qualifications and to ensure that they are capable of performing the work that you need done. Grounding systems play a vital role in electrical safety by providing a low impedance path for fault currents, ensuring the proper operation of overcurrent protection devices, and minimizing the risk of electrical shock. In the absence of a cold water pipe for grounding, alternative methods such as grounding electrode systems, ground rings, ground plates, grounding wells, and concrete encased electrodes offer viable solutions. Combining these methods can enhance redundancy and reliability. It is crucial to consider soil conditions, local regulations, and the National Electrical Code (NEC) requirements when designing and installing a grounding system. Consulting with qualified professionals and regular maintenance are essential for ensuring the effectiveness and safety of the grounding system.